Hello Science Alliance, hello my IGCSEs. We're skidding towards the end, you know, of Forces in Motion. We've only got, 3 weeks after this until Christmas, and then we'll be starting a whole new unit. So this is the lesson on impulse. It follows on very nicely from the lesson we did last week on momentum. You remember we were looking at how stoppable things are? We will recap. Anyway, I showed you these 4 equations and I said, can you just tell me what the letters mean and what the units are? So we'll go through this first. It's a nice gentle start. Here we go. There's quite a lot of maths in this lesson. So little u, maybe that was the hardest one. We talked about this in one lesson. Remember what little u is? V and u are both velocity. So they're both speed but with a direction. But u is an object's velocity at the start, or the fancy science way you would say it's initial velocity. So its unit is just meters per second because it's just speed with a direction, isn't it? So little v is velocity, but if you see a v and a u together, then u means velocity at the start and v means velocity at the end, or final velocity, okay? But they're both measured in meters per second because they're both a type of velocity. The little a was acceleration. Did you remember the units for that? Meters per second squared. Little s, some people were saying distance yesterday. Little s is displacement, so that is also a vector. It's like distance, but direction is important. M is for mass. Be careful. Still, even at A-level, I see people writing like capital M. No, it's a little m, which represents mass, and that is measured in kilograms, traditionally in physics. And F is force, and force is measured in newtons. And P, that we looked at last week, is momentum, and that is measured in kilogram meters per second. So if you got a bit further ahead and you were looking at the units for force, well, the equation F equals ma, force equals, oh wait, I've been teaching on Facebook all day, sorry, I can write forwards on YouTube. The equation F equals ma means force is the same as mass times acceleration. So if force is the same as mass times acceleration, the unit of force is the same as the unit for mass and acceleration. So the unit of force could be said to be the kilogram meter per second squared. Be careful, it's not kilograms per meter per second. You're timesing together mass and acceleration. So you want to times together the kilograms and the meters per second squared. So you just don't write anything to show that you're timesing them together. So the units of force are the Newton. We say that because it's a cool catchy name. It's a lot easier than saying kilogram meters per second squared. But the Newton and kilogram meters per second squared are the same. I don't know why for momentum the units are kilogram meters per second, and we haven't got a cool catchy name for that. Poor momentum, but there you go. Maybe you can make one up. Just don't write it in your IGCSEs. All right, so hopefully, I was going to say a simple task for you. It's maybe not that obvious, but just FYI. Can you write a simple equation for something's initial momentum? It's momentum at the start of a situation. How can you have a look at those equations and think, how would you write a simple equation for the momentum something has at the start, its initial momentum? Doesn't matter if you can't, because I'm going to tell you. So an equation for the initial momentum would be P equals mu, right? If momentum equals mv, that could be said to be like final velocity. So yeah, P equals mu would be saying the initial velocity. Right, we've got quite a lot of maths to do today, so we're going to start really slowly. We can play around with these equations and put them inside each other. For example, 3 times 2 equals 6. Yes, 3 times 2 equals 6. 6 divided by 6, 6 sweets shared out among 6 people is 1 sweet each, right? So that's 6 divided by 6, that 6 there is a 6. Told you we were starting simple. And that 3 times 2, that is also 6. Is that okay? So can you see how we could replace one with the other? We could get rid of the 6 in that last equation and replace it with 3 times 2. And that would be giving us the same answer. Yeah? Is that all right? That's all we're doing today. We're just building up from that. Okay, Can you throw a ball for me, please? Well, maybe you didn't have a ball. What I said was, please can you bring some scrap paper? We're very accessible here at Theatre Science. I don't assume that you've all just got footballs and tennis balls or whatever lying around. So just get a piece of paper, please. Piece of scrap paper and scrunch it up. This is going to be your ball. What I would like you to do is to just throw your ball up and down in the air and think about, well, actually, no, don't throw it up and down in the air. First of all, just imagine that you're going to throw it. So just act out throwing a ball, but don't actually throw it because you're going to have to get up and get it. It's a whole thing. So just act out throwing a ball, but really imagine you're throwing this ball. Can you tell me which one of these things that I've written on the board, or which of them, are changing if you hold the ball still and then you throw it? You move your hand forward. Which one of these things are you changing about the ball? I've put one of them as just question marks because there's something that we haven't mentioned yet that is really important and has to do with impulse. So force, acceleration, mass, velocity, initial velocity, final velocity, momentum. Which one of these things are changing? Which one of these things, which of these, I keep saying which one, sorry. Could be all of them. What's been affected by you? What are you changing about the ball when you throw a ball? Force, mass, velocity, acceleration, momentum. Pull you back up. In this Facebook lesson yesterday, I was just doing it was great telly, just doing this a lot with a furrowed brow. What are you changing? What is happening? Well, it started off still, did the ball, and then it started moving, didn't it? So straight away we know that its velocity has changed. It started out with a velocity of 0, and now it has some velocity. If its velocity has changed, like in this case it's sped up, then straight away you know it's accelerated, right? Because acceleration is just how quickly something changes its velocity. Is that all right? So the change in velocity... Oh, I've done it again! Did I do that before? Do I keep writing backwards? I'm really sorry. We have looked at this before, the change in something's velocity. Are you okay if I just write a cool little triangle to mean change in velocity? The change in velocity is just the difference between its initial velocity and its final velocity, right? So you could write change in velocity equals final velocity take away whatever its velocity was at the beginning, right? So that's the change in velocity, how much its velocity has changed. And that's measured, well, it's a velocity, so it's measured in meters per second. Whereas acceleration is how quickly it has changed velocity. So something could go from 0 to 20 miles per hour over a really long period of time, or it could just go from 0 to 20 miles per hour really fast. So that would be a different acceleration. Is that okay? And acceleration is meters per second, right? So what I wanted to think about was just what some of these equations actually mean. So you've changed the velocity of the ball, so you've accelerated the ball. In that case, so hopefully you're telling me that its momentum has changed as well, because it used to have 0 momentum we looked at last week because it wasn't moving. Momentum is its mass times its velocity. So its momentum, if velocity is 0, is going to be 0, and then it gets some momentum. What else are you changing? Well, I was going to say there are 0 forces acting on the ball. Obviously that is not true, is it? On a still object, gravity is still pulling it down. Your hand is pushing it upwards. What can I say about the forces acting on the ball? Come on, it's revision. Oh, something about the ball is 0. The resultant force acting on the ball, like the overall force, all the forces added together, the resultant force is 0. It's staying still, so all the forces on it must be balanced. And what you're doing is you are applying a force, right? So you're making it the resultant forces in that direction. So, set right forwards, Lara, come on, it's not that hard. So we've got this equation, F equals ma. It's not actually, you always say F equals ma, but I think a nicer way of writing it, if you want to actually understand it, is A equals F divided by m. So throw the ball with not very much force. Don't throw the ball very hard. What happens? Well, you don't get a very high final velocity, do you? So it hasn't accelerated very much. When f is small, this number is small, right? Makes sense. Loads of sweets, shared out between 3 people, the answer is loads. Not many sweets, shared out between the same amount of people, it's fewer sweets. When this number gets small, this number gets small. That's what I'm saying. If this number gets big up here, if force is really big, what happens to acceleration? It gets bigger. Yes, it's not rocket science. Well, it sort of is rocket science, but rocket science isn't the hardest branch of science. So when the force gets big, the acceleration gets big if the mass is the same, right? The mass of the ball is the thing, in fact, the only thing on this list, wasn't it, that is not changing. Everything else is changing about the ball, but the mass of the ball isn't changing. So you apply a bigger force, you get a bigger acceleration, and you know that if you picked up a bowling ball, which had a really, really, really high mass, then if you wanted the acceleration to be the same as when you were throwing this tiny little paper ball, well, if this has suddenly got big, and you want that to stay the same, this number has to get big as well. So you'd have to throw a bowling ball with a huge amount of force to get the same amount of acceleration, right? Phew, okay. Can you please now throw your ball up into the air and catch it a few times? Yeah? Have you done it? You done it? You got a feel for that? Can you please do that again? But can you imagine that the ball is a little kitten? Maybe your friend is high up and they are passing you this kitten, I don't know, and they just have to drop it. So you're catching a tiny cute little kitten. Really feel it. Really imagine that the ball is a kitten. I'm not going to do it because I don't want to affect you. What are you doing? Throw the piece of paper up and down. Now imagine that the ball is a precious little kitten. Really pretend that it is. Has the way that you're catching it changed? And yes, you may also like this video if you like. You could do that too. Like, subscribe, and catch a ball pretending it's a kitten. How are you behaving? What's different? If you are finding that you are behaving in a slightly different way, you might have found the answer to what was missing in this list of things. Something else is changing. Something else was changing as you threw that ball or pretended to throw that ball. Are you finding people were using the phrase cradling yesterday on Facebook, which I thought was a great word. Are you finding that if it's that you're cradling it, you're supporting it as it comes down? Is that what you're doing when you just throw a ball? I knew that was going to happen. It's okay, I have an infinite amount of scrap paper. When you just throw a ball, you probably find that your hand is just stopping it straight away. Whereas if you imagine it's a kitten, you're sort of doing a little drop. Why are you doing that? Why has life taught you that that's a good thing to do, to kind of hold it for a little bit longer on the way down? The answer is time is changing. And if you change time, you change other things as well. Come on, let's get into it. Let's learn about what impulse is. Right. All these equations that we've looked at, they're not about just plugging in numbers, people. No, equations help us to see how nature behaves. They help us to think. So have a look at this one. Final velocity equals the velocity at first plus acceleration times time. We can rearrange that a little bit, right? Let's take the u from this side and stick it on the other side. So now we've got v minus u equals at. Hopefully you can see that those are both the same equation. What does that actually mean? Well, we've got a v minus u here, and we have just looked at that actually. I just wrote that on the board. What is v minus u? What's the final velocity? Take away the initial velocity. It's the change of the velocity of the thing, right? So what this equation is telling us is the change of the velocity of a thing depends on, or is exactly the same as, how long it accelerates for. It's acceleration times the time. Okay, let's dig a little bit deeper. Instead of writing v minus u then, let's write change in v, because we all know that that means change in velocity, right? So the change in something's velocity equals at. So we can just rearrange that. Change in velocity divided by time equals acceleration. Okay. Again, we've seen this equation before. The acceleration of a thing, how fast it speeds up, is its change in velocity divided by time. And we know that f divided by m equals a... gasp! Guys, what can we do? Do you remember that easy little example with the sixes earlier? Look, we know that f divided by m equals a, and we know that change in velocity equals over t equals a. So let's just get rid of the a's and write change in velocity divided by time is the same as force divided by mass. Are you still with me? This is taking me right back to my physics days where it was just me sitting in a classroom and everyone else around me working and the teacher on the board like, numbers, 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 letters, numbers. Do you see? And I'd be like, no, I don't see. Very nearly in tears. So if that's you, don't worry. It's gonna be fine. We're just gonna go through it slowly, okay, all together. So we've ended up with the change in velocity of a thing divided by time equals force divided by mass, because both those things equal acceleration. So they're all equal in the same thing. Right. Okay, let's press on then. Whew. Are you okay with rearranging equations? You should be really for doing IGCSE Physics. If something's on the bottom on one side, you can move it to the other side by putting it on the top. So change in V divided by M equals F over M can become change in V times M equals Ft. You just take the M off the bottom and stick it on the top on the other side, and you take the T off the bottom and you stick it on the top on the other side. Okay, that's just a simple rearranging. That's the same equation. So change in velocity times mass equals force times time. Okay, we have got there. This might look really weird, but it does make sense if you think about what we did last week. Let's do a little flashback to last week. So momentum equals mass times velocity. Okay, we looked at how hard something was to stop was to do with its mass times its velocity. So just going to... You remember about momentum? So force times velocity equals how hard something is to stop. So like a bullet, very, very small mass, very big velocity, just as hard to stop as an elephant with a really big mass and a very slow velocity. Yeah? Right, good. So we've got change in velocity times mass up here, which is momentum. So we've learned that. So that bit is momentum. Let's do a little recap from last week. An elephant, for example, would hurt you more than a mouse if they ran into you at the same velocity, because the elephant is harder to stop. And in physics, we said this idea of something being hard to stop is called its momentum. So when you stop the elephant, you change its momentum. Is that okay? Obviously, like if you stop it, then you are changing its momentum because you change its speed, its velocity, and velocity affects momentum. So here's where my PowerPoint gets all super fancy, right? Don't try this at home, kids, but if you put yourself into the path of a moving elephant, what are you doing? You're applying a very small force to the elephant over quite a long period of time, right? And that causes the elephant's momentum to change. Eventually, don't try it, but if you stepped into the path of a charging elephant, you would be applying a very small force, so over a long period of time, its momentum would change. If you got a load of buddies, again, don't do it, but if you got a load of buddies together and you all stood in front of the elephant, you would be applying a larger force, right? You'd be pushing harder on the elephant, so it would take less time for its momentum to change. Let's talk about that again without using elephants. So we've got the equation that we just looked at. Force times time equals mass times change in velocity. Force times time equals momentum. For a car's momentum to change from like 10 kilogram meters per second to 0, you could apply a big force over a very short period of time. For example, if the car like bashed into a castle, that would be a big pushing force. Small period of time, the car would stop. Or if it, say, rolled onto some grass, you would get the friction of the grass, which is quite a small force, applied for quite a long period of time, and they would both change the momentum of the car. So we got there. Ft is called the impulse. If something's momentum changes, it experiences an impulse. It experiences a force over a certain period of time. And the impulse, this is a bit that's a bit weird. The impulse causes the change in momentum. Applying a force over a certain period of time changes the momentum of a thing, but it is also equal to the change in momentum of a thing. So I've just given you this question as an example. I wasn't really expecting you to answer it, but it's kind of a waste of a question not to just hover it in front of you for a few seconds and give you some brain exercise. This is the sort of thing you might see in an IGCSE. A cat of mass 4 kilograms falls onto a sofa at 3 meters per second and stops. What is its change in momentum? So that's from last week. And how much impulse has it experienced? Remember, impulse is force times time. And if it experiences a force of 6 newtons, how long did it take the cat to stop after it hit the sofa? So again, I've just put this to give you an example of how to work through a question, and then I'll give you one after this. But I'm just going to be silent for like 10 seconds to let you think about it. If you're bored, you can always like and subscribe. I mean, or obviously if you were bored, you'd probably just turn off. But like and subscribe before you go, yeah. All right, well, I'm just going to go through this one because, like I say, this one was really just to show you how to do it. There's a couple of different ways you could do this first question, actually. A cat of mass 4 kilograms falls onto a sofa at 3 minutes per second and stops. What is its change in momentum? You could have used this equation and found the momentum at the start and the momentum at the end and taken them away from each other, which is what I've done here. The initial momentum is mass times velocity, which is 4 kilograms times its initial velocity, which is 3 meters per second, which is 12 kilogram meters per second, and its final velocity was the same mass, obviously, but times 0 because it stopped, which is 0 kilogram meters per second. And then you could say that, well, the change in momentum is like the difference between those numbers, which is 12 kilogram meters per second. Actually, I'm just seeing, obviously, you could use this equation as well, couldn't you? You could say, okay, I can see that the mass is 4, the change in velocity is from 3 to 0, so I know that that's 3, and then you would just end up with, if you know that impulse is the same as change in momentum, you could just say it's mass times 4 times 3, which is 12. Anyway, how much impulse has it experienced? This is the weird thing. It's the same because force times time is impulse. And that is exactly the same as something's change in momentum. So it's just the same. It's 12 kilogram meters per second. If it experiences a force of 6 newtons, how long did it take the cat to stop after it hit the sofa? What are we using for that? So we've got the force of 6 newtons. We're looking for how long. So we're looking for the time it took to stop. So we need its change in momentum, but like a lot of IGCSE questions do, they've asked you to work that out already. So we can just go, all right, Ft equals change in momentum. So T equals change in momentum divided by F. We know that change in momentum is 12 kilogram meters per second. So it's 12 kilogram meters per second divided by 6 newtons, which is 2 kilogram meters per second per newton. I always say to you to check the units. In this case, we're just going to say, yeah, that is 2 seconds. If you want to go back and work out why the second is the same as the kilogram meter per second per newton, go for it. Good for you. I should say, some of you who have done this a bit before will be noticing that I haven't put minus signs in when technically I should have done, right? Momentum is a vector. So really, if I'm doing the change in momentum, I should have done the final momentum minus the initial momentum, which would have been 0 minus 12, which would have ended up with minus 12. That's completely fine. I'll explain why that's fine at the end of the lesson. The minus sign or the plus sign on a number, which is a vector, is really just telling you the direction. So in an exam, it would be fine. Technically, that should be minus 12, shouldn't it? Because 0 versus 12. Yeah, we'll talk about that later. Right, can you try these, please? If you've been to my website, you've downloaded my free printouts, you've got these in front of you, but if not, don't worry about it. You can just read it from the board. So impulse, Ft, equals mass times change in velocity, which is the change in momentum of a thing. And P equals mv, right? A bird is at rest, thinking about eating wormy. Gasp! We never use wormy in worksheets anymore. We need to. Wormy is the theatre of science mascot. So there's this bird at rest. It's thinking about eating wormy. So wormy, basically, she nuts it. She whacks it on the head. If the bird's head has a mass of 0.5 kilograms, I've been kind, right? I could have said 500 grams, but you need to use the number 0.5 kilograms because it's that's the unit you use. If the bird's head has a mass of 0.5 kilograms and moves away from wormy at 6 meters per second, what was its change in momentum? And what impulse has been delivered to the bird's head? Question number 3. If wormy was in contact with the bird's head for 3 seconds, how much force did she hit it with? If wormy was in contact with a bird's head for 3 seconds, how much force did she hit it with? And number 4, a trainee acrobat has a mass of 60 kilograms and travels at 3 meters per second. What is his momentum? And 5, if he splats, sorry, it's not a very nice word for a human, but if he splats into a padded wall with a force of 45 newtons, how long does it take him to stop? And question 6, 6 is a hard question, which will reveal an important point. A ball hits a wall at 10 meters per second and bounces off the wall at 6 meters per second. A cake hits a wall at 10 meters per second and sticks to it. Which one has the biggest change in velocity? And I've helpfully written careful. So yeah, be careful. Well, I'm going to do them behind you as well. You're all okay with the fact that impulse is just force times time, right? We're going to talk a bit more about this when we finish this question. I finished, but obviously I wrote the questions and I taught this lesson yesterday, so I'm going to give you a few more seconds. And then I'll go through, I mean, obviously you don't need to have done all of them. but then I'll give you a little bit more time to ponder over number 6. I'll tell you what, I'll go through the first couple, and then I can rub my answer off the board and write the answer to number 6. So a bird is at rest, thinking about eating wormy. She whacks it on the head. So basically, this thing has just had the bird's head is the thing. It's just had a force applied. It's got a mass of 0.5 kilograms, and it's moving. It was still, and now it's moving at 6 meters per second. So what is its change in momentum? If we've got its mass, we know what its starting velocity was. It was 0, and we know its final velocity is 6 meters per second. So I have written, and you could have done it a few different ways. I've written initial momentum, right? Initial P, momentum at the start, is mass times velocity. So 0 meters per second times the mass, which is 0.5. So you end up with the initial velocity being 0. The initial velocity is 0, and so the initial momentum is 0 as well. And the final velocity is the final momentum is its final velocity, which is 6 meters per second times its mass, which is 0.5 kilograms. So I've just put the change in momentum is the difference between those two numbers, which is 3 kilogram meters per second. What impulse was delivered to the bird's head? Well, if I was writing it in an exam, I'd try and be really obvious. So I've written impulse equals F times T, which is the same as the change in momentum. So it's the same. It's 3 kilogram meters per second. Isn't that all right? For question number 3, if Wormy was in contact with the bird's head for 3 seconds, how much force did she hit it with? Wormy was in contact with the bird's head. How much force did she hit it with? Right, so we're looking for force. So I need to show that I know how to rearrange equations. So I've written Ft equals change in momentum. And then I've rearranged that because we're looking for force. So force equals change in momentum divided by t. So the change in momentum, we just worked that out, is 3 kilogram meters per second. And Wormy's in contact with the bird's head for 3 seconds. So the answer is she must have whacked it with a force of 1 Newton. Number 4, this acrobat has a mass of 60 kilograms, travels at 3 meters per second. What is his momentum? It's just mass times velocity, isn't it? Which is 60 kilograms times 3 meters per second, which is 180 kilogram meters per second. And if he splats into a padded wall with a force of 45 newtons, how long does it take him to stop? Again, Ft equals change in momentum. So if you rearrange that, you get T equals change in momentum divided by force. So the change in momentum is, I haven't bothered to show it actually, but he's stopped, so his momentum has become 0, so it's just the same. 180 kilogram meters per second divided by 45 newtons, which should have given you the answer of 4 seconds. And then this ball cake question is really hard, I think. Sorry, I've just realised I did that thing, didn't I, where I said that I was going to just go through the first couple, and then I went through them all. Sorry about the spoilers. I will be setting you some of these questions for homework. There's loads of these available. There was loads of questions that I couldn't set you last week because they were about impulse. They tend to combine impulse and momentum. Right, I'm going to quickly draw this ball cake scenario on the board while you maybe finish thinking about that. I have given you a bit of a clue earlier, but only a bit really. Alright, let's have a look at it. So this ball hits the wall at 10 meters per second, and then obviously, well, I'll flip you around. Let's think about it together. So the ball hits the wall at a force with a velocity of 10 meters per second, and then it bounces back off the wall with a velocity of 6 meters per second. Whereas this cake hits the wall with a velocity of 10 meters per second, and then stops. So its final velocity is 0 meters per second. What you might think is that you might have worked out, well, the difference between 10 and 6 is 4, and the difference between 10 and 0 is 10. So the cake has had the biggest change in velocity. But that is not true. It's actually the ball. And why it's the ball was hinted at very briefly in a couple of lessons. We're talking about velocity, right? Velocity has a direction, and one of the ways that you often show direction with in physics is just with whether it's a minus or a plus sign at the start. So if this ball is travelling in this direction, let's say straight ahead with a velocity of 10 meters per second, if it's now travelling in the opposite direction, then what you've done is you've said, okay, I'll say that the forwards direction is positive. So if it's going in the opposite direction, backwards, you need to make it the opposite sign as well. So really, technically, and this is me because I tend to get a bit sloppy with this actually, really the velocity of this one, if it's travelling the opposite direction, would have to be 6 meters per second, minus 6 meters per second. So the difference there is 16 meters per second, whereas the difference between 10 and 0 is only 10 meters per second. So the answer was the ball. And if you're confused, it works the other way as well. It's what we call arbitrary. Like, you can decide. That's why I was saying in the previous questions, don't worry if you've got a minus sign or a plus sign, because you just decide which way is forward and which way is backwards. You could say, well, I want to say that forwards the velocity is minus 10. Yeah, you absolutely could say that. The forwards velocity is minus 10, so the backwards velocity is then the opposite, and it's positive 6. What's the difference, picture your number line, between minus 10 and 6? It's still 16, isn't it? So it still works. And it's like with the question about the cat. Like, I suppose strictly speaking, you can say that downwards is positive, or you can say that upwards is positive. It doesn't matter as long as you sort of stick to one thing. Yeah, right. So that's it. Very quickly, because one of the specifications, and I feel like it's EdXL, slips in this little bit about road safety, and it's quite interesting. Sorry, that was just me checking the time. Sorry, that was me checking the time again. Every time I check the time on my phone, it freezes, so I won't do that again. Yeah, they mentioned road safety and how this relates to impulse. I mean, I know I'm biased because I'm a physics teacher. I think this is really interesting. What has road safety got to do with impulse? So impulse is 4 times time, which is the same as the change in momentum. Here is a lovely looking person, so happy, sailing through the countryside on their bike, wearing a bike helmet. Why is that a big clue as to what road safety has got to do with impulse, what we've just talked about? I think I'm just so happy that it's really easy to think of real world examples for what we've been talking about. It's not always the case in physics. Here's how this actually relates to the world around you, children. What has road safety got to do with impulse? If you can't see the screen, a pen has appeared from the left and is pointing at the bike helmet. Well, what it is actually, I'm not going to do this. I'll set you those questions for homework. What it is if change in momentum, can I just write change in P? If your change in momentum, your change in P, is equal to the force times the time. Actually, I'll tell you what, I'll do it here because it sort of helps to be able to think about it all in a row like that. Imagine that you're on a bike. Imagine you're not wearing a helmet. Obviously that would never happen, but imagine you're on a bike, you're not wearing a helmet, you fall off your bike. What happens to your head? Well, your head has momentum, right? It falls off the bike, so it has a velocity, it moves towards the ground, it hits the ground, and it stops. So your head experiences a change in momentum, which is equal to the amount of force that you experience times the amount of time that force is applied for. So if you're not wearing a helmet, you probably stop really quickly. This change in momentum happens really fast. So this time number would be small. Now what happens if momentum, it's going to be the same, isn't it, right? Whether you're wearing a helmet or whether you've got a pillow strapped to your head or whether you're not wearing a helmet at all, you're still going from moving to not moving. So if momentum stays the same, change in momentum stays the same, but the time is very, very small, what must happen to this number? It must be very big. Yes. So this equation sort of explains why if you're not wearing a helmet, it really hurts because you experience more force. Whereas if you're wearing a helmet, like something padded, that increases the amount of time that the force is applied for. It increases the amount of time it takes for your momentum to change, I should say. So the longer it takes for your momentum to change, the bigger this number is, the smaller the force is. And there's loads of examples of this happening. So here's a question for you, just before we go. Has this car done a good job? This car has been in an accident, it's hit a wall, and the front of it is all smushed up and bent. Has it done a good job? Would you be wanting to file a complaint about the design of this car? What do you reckon? The answer is, yeah, it's done a great job. What it's done is it's made, the car has changed momentum. The car has gone from moving to not moving. So the car has experienced a change of momentum. And what that bit is at the front is it's a crumple zone. And the crumple zone is there to make the change in momentum happen for as long as possible. And you see this all over the place, but it does really relate, especially to car safety. Child seats in cars, crumple zones, seat belts, airbags, they all use this principle of impulse, that if you can increase the time, make this number bigger, then the force gets smaller, so the person isn't as likely to get injured. And there's loads of examples of this. It makes me a bit queasy just looking at this picture, but here is a person bungee jumping. It doesn't look fun to me anyway, but imagine how much less fun it would be if there wasn't any give, if this wasn't an elasticated rope, if it was made of, I don't know, if it was a chain. Oh, let's not think about it. But anyway, that's impulse happening, isn't it? The elasticated bungee line is elasticated so that when the person changes momentum, they stop. It takes a long time for them to stop. It just slowly stretches and stretches and stretches, because the longer it takes them to stop, the less force is yanking them and less it's hurting. If you've heard the phrase roll with the punches, this is something that boxers do. It's a phrase now to mean that if you roll with the punches, you sort of adapt to a situation. But it is actually something that boxers do. If boxers, don't try this at home, I guess, unless you like boxing. When boxers get punched in the face, rolling with the punch means relaxing your head and letting your head move backwards. Because if you tense up, then you're stopping that hand's changing momentum is happening very quickly. So you're experiencing a high force. Whereas if you allow that fist to be in contact with your face for longer, the force is smaller. And finally, I love it when it all fits together. We've been doing the human body lessons over in all ages lessons. So if you're watching live, we just looked at how the nose has got cartilage at the front. There are some nose bones, like the vomer, but it's at the back. The front is cartilage. And why is that? I briefly mentioned it at the time. You want the front of your nose to be a little bit squishy, because if you hit something, then you want the change of momentum to happen over a longer period. So you get it, don't you? You get it. I've said enough. Squishiness equals less force, more time. Whew, right, that is the end of the lesson. Thank you so much for joining me. I'm going to go over to my Facebook page, as I always do when I'm live on YouTube, because I do not have comments on YouTube. But on Facebook, there is a comment at the top now on my Facebook page, Theatre of Science, just saying if you are watching live and you want to ask me any questions, or to shriek, "Stop writing backwards!" at me, then you've got a place to do that. It's important that you have an outlet for that. So let's go and see if anyone said hello. If you are enjoying these lessons, you can pay me for them. It's such a weird business model. This just works out really well. So I do everything for free. I've said that I'm not going to charge for anything that will help someone to pass their exams. That's the rule that I've got in my head. And so far, I haven't had to break that rule. So the printouts for all the lessons are free. All the actual lessons are free. The all ages lessons are free. They're all stored on my website for watching on Catch-Up. Nothing is behind a paywall. It's all accessible for everyone. But the people who sign up to support me receive an incredibly good but really unreliable science magazine. A little package will come through the door if you choose to support me, with some rainbow glasses in and some past Theatre of Science magazines, which are very good. Did I mention how good they are? And incredibly unreliable. They take me ages to write. Hello, Bastian. No way, Bastian's here. And Chloe, got the units wrong, but so Bastian, this just it makes my heart go rainbows. Got something wrong, learn from it. Yes, it's so good to get stuff wrong in lessons. I mean, really, that's the whole point, because if you get stuff wrong in the lesson, you're not going to get it wrong in the exam. Understood that they should be added together. Yes, nice. Okay, excellent. That is really good. Oh, that printout looks good. I never get to see them actually printed out in colour. Hello, Chloe. Well, what was I saying? Oh yeah, something about supporting me and how that would be a good thing to do. Yeah, I think that was it. So if you go over to my About section now on YouTube, where you are, if you go to my About section, it links you to coffee, and you can support with £5 a month, and I will send you nice things. I feel like I was going to say something else, but I don't know, it can't have been important. Right, I'll be back next week, because like I say, we've got 3 more lessons on forces of motion. I've also got a pre-recorded lesson on the maths, which I thought might be helpful. You can just watch that in the archives section of my website if you like to, it's on YouTube already. So yeah, I don't think I'll reteach the one on maths, because it's a pre-recorded lesson with all like fun bits that pop up, and it took me forever to do. So if you want to watch that one, you can now. It's just in my archive section. But otherwise, yeah, 3 more lessons and then Christmas. So I'll see you next week. Thanks for coming. Bye. Wait, tried to stab the wrong side of my screen. I'll try that again. See you next week. Thanks for coming. Bye.